Hey everyone, and welcome. We're diving into the world of neutrinos today. You know, those super tiny, almost invisible particles that are constantly zooming through us and the entire universe. You guys have sent in some seriously cool research on neutrinos, so let's get into it, figure out why scientists find them so fascinating, and what they can tell us about, well, everything.
It really is incredible how much we've already learned about these neutrinos, especially considering they're so hard to detect. I mean, trillions are passing through you every single second, and you'd never even notice. They're like little ghosts. But thankfully, through some pretty ingenious experiments and decades of research, we're finally starting to uncover some of their secrets.
Yeah, those secrets sound pretty amazing, but before we get too deep into it, maybe let's start with the basics. What actually is a neutrino?
Okay, so picture the tiniest building blocks of the universe, like the absolute smallest things that make up everything. Those are called elementary particles. Neutrinos are one of these particles, just like electrons and protons that you've probably heard of, but with one key difference. They don't have any electric charge.
Okay, so no positive or negative charge. That's why they're called neutrinos.
Yeah, exactly. It's like saying tiny neutral one in Italian. And it's that lack of charge that makes them so tricky to study. They basically just pass through everything, interacting very, very rarely.
That makes sense. But if they're so hard to find, how did scientists even realize they existed in the first place?
Well, it all started with a bit of a puzzle. Back in the 1930s, physicists were studying radioactive decay, how some atoms break down over time, and they noticed that sometimes energy seemed to just disappear during this process.
Energy just vanishing? That doesn't sound right.
Exactly. It was a big problem because one of the fundamental laws of physics says energy can't just disappear, it has to go somewhere. So Wolfgang Pauli, this brilliant physicist, came up with a solution. He said there had to be a particle that we couldn't see carrying away that missing energy. He originally called this hypothetical particle a neutron.
Ah, so a neutron was causing the energy to go missing.
Well, sort of. It gets a little confusing because just a few years later, James Chadwick discovered an actual particle in the atom's nucleus. And guess what? They call that a neutron too.
Oh, okay, so two neutrons running around, that must have caused some chaos.
Yeah, a bit. To clear things up, they decided to call Pauli's particle a neutrino, meaning little neutral one in Italian. It was basically a smaller, lighter version of Chadwick's neutron. Pauli suggested that this neutrino was emitted from the nucleus during radioactive decay along with an electron. But proving that his theory was actually correct, that took decades.
Wow, so scientists actually predicted something they couldn't even see, and then it turned out to be true. That's pretty amazing.
It really is. And as if that wasn't mind-blowing enough, later research revealed that these neutrinos are even weirder than anyone could have imagined.
Okay, now I'm really intrigued. The research I sent over mentioned something called neutrino oscillation. And honestly, it sounds kind of like something from a sci-fi movie.
It kind of is. Imagine a chameleon that's constantly changing its color. That's basically what neutrinos do as they travel through space. They oscillate, which means they shift between three different flavors: electron, muon, and tau neutrinos.
Hold on, so they're changing their identity while they're flying through space. How is that even possible?
Okay, so this is where things get really into the realm of quantum mechanics. So buckle up. Basically, when a neutrino is created, it has a specific flavor, but it's actually a mixture of three different mass states. As it travels, the proportions of those mass states shift, and that makes it look like it's changing flavor. And here's the kicker. This entire process only works if neutrinos have mass.
But for the longest time, everyone thought neutrinos were massless, right?
Exactly. This discovery of neutrino oscillation was a huge game changer. It meant that those long-held beliefs were wrong. For these flavor changes to happen, each of those neutrino flavors needs to have a slightly different mass.
Wow, my mind is already blown.
Yeah.
And we're just getting started. So we've got these shape-shifting particles zipping through us all the time, and they're telling us something about the universe. What kind of information are these neutrinos carrying anyway?
Well, that's the truly amazing thing. Neutrinos come from all sorts of sources. We're talking about the sun, exploding stars, even the Big Bang itself. They're like tiny messengers traveling billions of light years across the universe, carrying information about these incredible events. And because they barely interact with anything, they bring us information that other particles, like light, just can't.
So by studying them, we're basically getting a direct look into events that happened billions of years ago.
Exactly. It's like having a front row seat to the heart of a star or the aftermath of a supernova explosion. It's incredible.
It's amazing, right?
Yeah. All that information packed into these tiny, tiny particles.
It's pretty mind-blowing. But how do scientists actually read these messages? I mean, if neutrinos can pass through almost anything, how do they even catch them, especially if they go right through detectors?
Yeah, that's the big challenge. It's not like you can just, set out a net and catch these neutrinos.
Right.
So what scientists have done is they've come up with some seriously clever methods to observe them indirectly.
Indirectly, okay.
One common way is to use these massive detectors, and they're filled with materials like water, or sometimes heavy water. And get this, they bury them deep underground.
Underground. Why go through all that trouble?
Well, it all comes down to reducing interference. Think of it like this. Imagine you're trying to have a conversation in a really noisy room. It's hard to hear anything, right?
Oh, yeah, for sure.
It's the same idea with neutrinos. By going deep underground, we can shield those detectors from a lot of the noise caused by cosmic rays.
Cosmic rays.
Yeah, these high-energy particles constantly bombarding Earth from space. They create a lot of interference.
Ah, I see. So the Earth itself acts like a giant filter.
You got it. And then by using materials like pure water, which have very low natural radioactivity, they can minimize interference even more.
So they're creating this super quiet environment just to listen for these tiny little neutrino signals.
Precisely.
But okay, even with these ultra-quiet underground detectors, how do they actually know when a neutrino has hit something? Because we can't see them directly, right?
Right. It's kind of like a cosmic game of billiards, We can't see the neutrino itself, but we can see what happens when it bumps into other particles. So when a neutrino interacts with an atom inside the detector, it can create other particles that we can detect, like electrons or muons.
Ah, so it's like a chain reaction.
Yeah.
The neutrino causes something else to happen that then sets off a signal we can measure.
That's a great way to put it. And these particles they create, they leave a trail of light called Cherenkov radiation. It's this really distinctive blue glow. And that blue glow acts as a sort of fingerprint. It tells us, hey, a neutrino interaction just happened here.
So it's like a detective story. Scientists have to sift through all this data looking for those flashes of blue light to identify a real neutrino event.
Exactly. And it takes a deep understanding of particle physics, how the detectors work, and of course, how to analyze all that data. But even with these amazing detectors and all the precautions, there are still limitations. There are only so many neutrinos we can actually detect.
Yeah, that makes sense. So what are some of those limitations?
Well, even the biggest detectors, they're still only capturing a tiny fraction of the total neutrinos that are passing through them.
Really? A tiny fraction?
Yeah, it's like trying to study an entire ocean, but you're only looking at a few drops of water. So to get enough data to really draw conclusions, it takes a lot of time. We're talking years, sometimes even decades.
Wow. That's some serious patience.
Oh, yeah. Neutrino research definitely requires patience.
I bet. So besides that, what are some of the big hurdles scientists are still trying to overcome?
One of the big ones is detecting those lower energy neutrinos. Most of the detectors we have now are really good at finding the high energy ones, like those from supernovae. But there's a whole world of low energy neutrinos out there that we're basically missing.
So it's like we're only hearing part of the story.
Exactly. And these low energy neutrinos, they could hold clues about dark matter and the very, very early universe.
Oh, wow, that's amazing. So scientists are trying to develop new ways to capture those then?
Oh, absolutely. They're always pushing the boundaries, trying to come up with new technology and techniques.
That's pretty cool. Okay, so we've talked a lot about how these neutrinos can help us understand the universe, but what about our understanding of physics itself? The research I sent mentioned that this discovery about neutrino oscillations, them changing flavors, that really shook things up in the world of physics.
Oh, it absolutely did. It really challenged some fundamental ideas. You see, for a long time, our best theory of how the universe works at the subatomic level, it's called the Standard Model of Particle Physics. And that model, it said that neutrinos were massless. But then this discovery of neutrino oscillations and the fact that they do have mass, it threw a wrench in things.
So these tiny particles basically forced physicists to rethink some of their biggest ideas.
Yeah, pretty much. It meant that the standard model was incomplete. We need to go beyond it, figure out a new theory that can explain everything we're seeing with neutrinos.
Wow. So neutrino research is really pushing the boundaries of what we know.
Absolutely. It's opening up whole new areas of research. It's so exciting.
I can imagine. Okay, this is all fascinating. But what are some of the biggest unanswered questions that scientists are still trying to figure out? What's keeping them up at night?
Well, one of the biggest mysteries is still nailing down the exact masses of those three types of neutrinos. We know there's a difference in mass between them, but we don't know the actual values.
And why is that so important to know?
Well, it's more than just a number. Figuring out those masses, it would be huge for our understanding of, well, everything. Particle physics, cosmology, the whole shebang. It could tell us about the hierarchy of masses in the universe, the fundamental nature of matter, and maybe even help us understand why the universe is made up mostly of matter and not antimatter.
Okay, so a seemingly tiny measurement could unlock massive secrets about the universe.
You got it.
Wow, that's pretty wild. And is that the only mystery, or are there other big questions about neutrinos?
Oh, there are plenty. Another big one is, are neutrinos their own antiparticles?
Wait, their own antiparticle? I thought every particle had an antiparticle, like a mirror image with the opposite charge.
You're right. Most particles do have a distinct antiparticle, but neutrinos, they're neutral. So it's possible, just possible, that they could be their own antiparticles.
Whoa. Okay, that's a tough one to wrap my head around. How do scientists even go about testing that?
They're looking for a really, really rare type of radioactive decay called neutrinoless double beta decay. If they find evidence of it, that would suggest that neutrinos are their own antiparticles.
So it's like a cosmic treasure hunt, looking for this super rare process that could reveal a fundamental truth about neutrinos.
Exactly. It's pretty amazing, isn't it?
It really is. And what about those sterile neutrinos, the ones that might be part of dark matter? What's the latest on those?
Ah, yes. Sterile neutrinos. They're hypothetical particles that don't interact with the weak force.
The weak force.
Yeah, it's one of the 4 fundamental forces of nature. So if these sterile neutrinos exist, they would be completely new particles beyond our current understanding of physics. And they could be a big part of dark matter, which is this invisible stuff that makes up a huge chunk of the universe.
If we're talking about a whole new type of matter, maybe even interacting with the universe in ways we don't even understand yet.
Yeah, exactly. Scientists are looking everywhere for them, but no definitive proof just yet.
It sounds like neutrino research is just getting started. So much we don't know, so many mysteries. But besides understanding the universe, are there any practical uses for what we're learning about neutrinos? I mean, could they do anything for us here on Earth?
That's a great question. It's true that most neutrino research is driven by pure curiosity, just wanting to understand how the universe works. But there are some really intriguing potential applications that are being explored.
Oh, really? Like what?
Well, one area that's super fascinating is using neutrinos for communication. Because they can pass through almost anything. Imagine being able to send messages through the Earth. Like straight through the core.
Wait, a neutrino internet?
Haha, yeah, something like that. They wouldn't be slowed down by the Earth's interior like radio waves, so theoretically you could have faster, more secure communication.
That would be incredible, a total game changer.
Right.
So are there any other practical applications scientists are working on?
Yeah, another really interesting one is using neutrinos to image the Earth.
Image the Earth? What do you mean?
It's kind of like how doctors use X-rays to see inside the human body. We could potentially use neutrinos to map the Earth's interior, figure out its structure and what it's made of.
That's amazing. How would that even work?
Well, different materials absorb neutrinos at different rates. So by analyzing those absorption patterns as the neutrinos pass through the Earth, we could create 3D images of what's going on inside.
So we could discover hidden mineral deposits, oil reserves, or even magma chambers under volcanoes.
Exactly. It'd be like giving geologists X-ray vision for the entire planet.
Wow, that would be an incredible tool.
It would revolutionize our understanding of our own planet. And those are just a couple of the possibilities. Who knows what else we'll discover as we continue to study neutrinos.
This is all really amazing.
Yeah,
It's incredible to think how much we've learned about neutrinos already. But I have to ask, how does all this research get done? It sounds expensive and complicated. Who's paying for all of this?
You're right. It's a huge undertaking. We're talking about massive detectors, cutting-edge technology, years of data analysis. It requires a global effort, with scientists from all over the world collaborating on these projects. It really is a global effort. It's inspiring to see, all these people from different countries, different backgrounds, all coming together to try to understand the universe.
Like a massive team effort, with everyone contributing their expertise to solve this giant puzzle. But yeah, I imagine it must be incredibly expensive to build and run these experiments.
Oh yeah, it definitely takes a lot of resources. We're talking billions of dollars sometimes. Building those massive detectors, developing new technology, and then, analyzing all that data, it adds up quickly.
So how do scientists convince governments and funding agencies that neutrino research is worth all that money?
Well, it's about showing them the big picture. It's not just about understanding the universe, although, I mean, that's a pretty big deal in itself. But it's also about the practical benefits, the spin-offs that come from this research.
Spin-offs, like what?
Well, for example, some of the technology that was developed to detect neutrinos has actually ended up being really useful in medical imaging.
Oh, really?
Yeah, it's helping doctors diagnose and treat diseases better. And then there's the data analysis techniques that they use for these huge neutrino experiments. Those are now being used in other fields, like finance and even climate modeling.
So it's an investment that ends up benefiting lots of different areas.
Exactly.
Okay, that makes sense. But even with all the money and resources in the world, what are some of the biggest challenges that scientists are still facing with neutrino research?
Well, as we've been talking about, figuring out the absolute masses of those three types of neutrinos is still a huge one.
Right, cracking that code would be big, wouldn't it?
Oh, yeah, it would be revolutionary.
So it's like a race against time, with all these scientists trying to figure out those neutrino masses. What else is keeping them up at night?
Well, another big question is a neutrino its own antiparticle? Or is it a different particle entirely?
That's right. That's that mind-bending idea we talked about earlier.
Right. It's crazy to think about.
Yeah, it is. So how are scientists actually trying to figure that out?
Well, they're looking for evidence of this really, really rare process. It's called neutrinoless double beta decay. And if they find it, that would be a pretty good sign that neutrinos are their own antiparticles.
So it's another piece of the puzzle, leading us closer to understanding the true nature of neutrinos.
Yeah, exactly. And then, of course, there's those sterile neutrinos, which we touched on earlier.
Right, the ones that could be a part of dark matter. What's happening on that front?
While the search continues, there are experiments happening all over the world, at nuclear reactors, particle accelerators, even in space.
Wow, that's amazing. So it seems like neutrino research is a constantly evolving field, with new discoveries and challenges popping up all the time.
It really is. There's so much we don't know and so much to explore. It's what makes it so exciting.
It sounds like it. It's amazing to think about all these scientists working all over the world, chasing these tiny invisible particles. And what they're learning is helping us understand the universe in a whole new way.
Yeah, it really is incredible. It's a reminder that we're still just scratching the surface, you know? There's so much more out there to discover.
Well, that's a pretty inspiring thought to end on. It's been a fantastic deep dive into the world of neutrinos, from their basic properties to their huge implications for how we understand the universe. Thanks for taking us on this journey.
My pleasure. It's been a blast.
And to everyone listening, thanks for joining us on this deep dive. If you're interested in learning more about neutrinos, there are tons of resources out there. Keep those questions coming, stay curious, and who knows, maybe you'll be the one making the next big neutrino discovery. Until next time, keep exploring.